everyone, my name is Blake, and I am going to make the review video about kinetic molecular theory, which is lecture 20. Kinetic molecular theory is it's basically how gas molecules move about. You know all their intermolecular forces, their composition. This is just how they move and how they interact with each other. Hence the name kinetic, everything moving around, molecular at the atomic level, and then theory, I guess. But then, so kinetic molecular theory, it's based off of these two charts, basically, because there's the gas properties very highly affect what kinetic molecular theory is, and some assumptions about gas molecules are put into how kinetic molecular theory was formed. So the basic gas properties that I feel like a lot of us know, but I'll go over, is that gases are expandable and compressible, and that means that they don't have a definite volume or a definite shape. Think of a balloon. When you have a balloon, when it's tied up, you can squeeze it and it becomes smaller, or you can stretch it out and the volume becomes bigger, but the same amount of gas is in there. So it doesn't have a definite shape or a definite volume. It's kind of amorphous. It just does whatever it wants. And then homogeneous. All gases are homogeneous mixtures. So when you blow air into a balloon, for example, you're not blowing in pure oxygen. It's carbon dioxide, you got some nitrogen in there. So you got a bunch of different stuff in there. But all of them are all of the different gases are spread out equally. It's not like in one section of the balloon, it's all carbon dioxide. In one section, it's all nitrogen gas. They all intermix freely with each other, so they're homogeneous. And because there's no definite shape or no definite volume, they fill containers. Because, for example, when you pour water into a bottle, it won't always fill the bottle. Because if you pour like 1 cup of water in a 2-cup container, it's half full. But the thing with gas is no matter how much gas you put into a container, it always expands and equally spreads out, and it fills the entire container. There's not a specific part of the container that is in vacuum or whatever. It completely fills it because it is expandable and there's no definite volume or shape. And then next assumption is that, or the property is that it has a lower density than solids and liquids. And that's pretty self-explanatory, but the lower density than solids and liquids, it just means that basically it's more spread out, and in the same amount of space, there's going to be less mass. And then this one, exert outwards pressure, that is because of Newton's third law. Because think about it, when a gas is in a container, the container is exerting a force on these gas molecules to stay in the container, and it's expandable, so it will always reach the edges of the container. So since the container is exerting a force to keep it in there, the gas molecules are exerting a force back on the container. Newton's third law, all forces have equal and opposite reactions. So the gas will exert pressure on the side of the container. And these properties lead to some assumptions we can make about gas molecules when we're applying kinetic molecular theory. For example, gas molecules have very small volume compared to container. Individual gas molecules are so tiny because they equally spread out. You can kind of treat them as points. They won't have a whole lot of volume. Also, they have random and constant motion. That just means that if you have some gas in a container, there isn't going to be some gas molecules that are just chilling on the side and they're not doing anything. All gas molecules are randomly and constantly moving. You don't really know where they're going to go. And then elastic collisions. This means that in a container, since all of these gas molecules are moving, they hit off of each other perfectly and kinetic energy is preserved. So that means that everything is running around in a container. The kinetic energy won't decrease, it's always perfectly transferred. And that's not always the case, but we can make this assumption. And then no intermolecular interactions. So I have a little asterisk on there because that's not always the case. There is always a little intermolecular forces between atoms, but we can assume for ideal gases, if we want to idealize a gas as an ideal gas, that there are no intermolecular interactions and that they're just points bouncing around. And then there's a different formula for gases that you don't want to treat as ideal, that are a little more polar, but that is in another lecture. And the average kinetic energy of the gas is proportional to the temperature, and this makes sense because temperature is a measure of the kinetic energy of gas molecules, or of anything. So the temperature will directly tell you the average kinetic energy of the gas in a container, and every gas molecule is not moving at the same speed, does not have the same energy, because some are moving a little slower, some are moving a little faster, but the temperature measures the average. So now that we know the assumptions and the properties associated with kinetic molecular theory, we can start to apply it to equations and actual numbers in math. So remember that in a massive gas, all of the molecules of gas, they're not moving at the same, they don't have the same kinetic energy. But so the average kinetic energy of a massive gas is equal to 3/2 times R, which is a constant, times T, which is the temperature in Kelvin. And that is also equal to 1/2 times the mass of the massive gas times the root mean square speed squared. And the root mean square speed is associated with the velocity of all of the gas molecules. And this equation for kinetic energy makes a lot of sense because the normal equation for kinetic energy when you're dealing with physics or an object moving is 1/2 times the mass times the velocity squared. And this is very similar to it because this is representative of velocity. So how you get the root mean square speed, that is the square root of 3 times the gas constant R times the temperature in Kelvin over the molar mass, which is M. And M is in moles per kilogram. So, or no, it's not in moles per kilogram, it's in kilograms per mole, my bad. So, and the root mean square speed also means when you take all the speed of the individual molecules, you add that up in a way and you get the root mean square speed. So you have U1 and U2, those are representative of the velocity of individual gas molecules. So you get the velocity of one gas molecule, square it, add it to the square of another gas molecule, and keep adding it, until you have all of the molecules of gas accounted for. And then, so you take the average of the squares by dividing it by the number of gas molecules, and then you take the square root of that. That's the root mean square speed. So what this means is that with the root mean square speed in a gas, the root mean square speed is higher when the temperature is higher. And that makes sense because temperature is on the numerator. So as temperature increases, then the root mean square speed increases. So I drew this little graph, and the x-axis is speed, and the y-axis is number of molecules. Sorry, it's a little hard to read in the red. I just want a little variety in the color. So imagine that these lines represent the same gas, but this is at a lower temperature, the red, and the green is in a higher temperature. So when the temperature is lower, that means that the speed is lower. And but when you have a higher temperature, the speed is higher because it's further along that axis. But it also means that as the speed is higher and the temperature is higher, the number of molecules at that top speed is lower. The distribution is wider, as you can see. It's more evenly spread out. But in this one, where the root mean square speed is lower, because the temperature is lower, more of the molecules are closer to that top speed, or to the average speed. So this equation also implies that when you have a higher molar mass in kilograms per mole, you have a lower root mean square speed. So imagine that this is a heavier gas like O2, the red, and think that this green line is H2, a much lighter gas. So since this gas is heavier, and these are both at the same temperature, this has a lower root mean square speed, but more of the oxygen molecules are going to be at the average speed than the hydrogen molecules. Not a lot of the hydrogen molecules will be at the average speed, but the average is much higher. Another aspect of kinetic molecular theory is diffusion and effusion. So diffusion is when a gas is in a container and it evenly spreads out in the container. So it likes to move from high concentration to low concentration until it's all evenly spread out. And diffusion is just effusion is just diffusion, but it's through when it's spreading out its concentration through a very small hole. So this picture of effusion is when you have an area of high concentration of gas. The gas is represented by the blue dots, and then a low concentration of gas. And this is a wall with a very small hole in the middle. So effusion is diffusion, but just the molecules are diffusing through a very tiny hole in a container. So effusion and diffusion, this happens because gases fill their containers. That is one of the properties, because it always wants to touch the sides, evenly spread out. So it'll move from high concentration to low concentration. So a real world example of this is when you're blowing up an air mattress with your mouth. When you blow in the air, the mattress evenly spreads out and rises as you blow air in. One part of the mattress, like a small part of it, doesn't pop up full, it isn't fully blowed up, and then the rest of the mattress doesn't just pop up fully inflated until it reaches the end. It gradually rises all together, and the mattress level is always the same throughout when you're blowing up the mattress. So gas will always try and flow from high concentration to low concentration in a container equally, but it does take a little bit of time for the gas to travel from high concentration to low concentration. So that is when you get the rate of effusion and the rate of diffusion, which is measured in moles per second. So how many moles can move per second? So this brings us this nifty little equation called Graham's law. So the rate of effusion or diffusion of a gas over the rate of effusion of another gas is equal to the square root of the molar mass in kilograms per mole of a gas over the molar mass of kilograms per mole of gas A. So this also means that the rate of effusion or diffusion is proportional to the square root of 1 over m. So this implies that if you have a larger molar mass, then the rate of effusion or diffusion is smaller, which means it travels slower. So there are less moles of that substance per second traveling, or going from one side to one side. So, and this means that a heavier gas like oxygen, compared to, well, in the grand scheme of things, I guess oxygen isn't too heavy, but oxygen is heavier than hydrogen gas, so has a higher molar mass. So the square root of 1 over the higher molar mass of oxygen, that's going to be smaller than the rate of effusion or diffusion of hydrogen gas. So that means that the rate is going to be smaller for oxygen, so it's going to travel slower. And that makes a lot of sense because heavier objects require more energy to move, and they generally travel a lot slower than the lighter objects that take less energy to move. The last topic for lecture 20, kinetic molecular theory, is the concept of pressure. And pressure equals force over area. So, to think about pressure, say that you have a 1-inch square space. I'll draw this out. You have like a 1 square inch space. And then you have, let's say, a 5 square inch space. That's probably more than, it's probably not proportional, but you get the gist. 1 square inch, 5 square inches. Let's say you apply 5 pounds of force to both of the areas. So you both have the same amount of force, but for this you have a ton less area than this one. This has a lot more area. So this one has a lot more pressure on it because each spot on the square has to support a lot more force than here because the force is more evenly spread out. So this has a lot more pressure than this one, even though the same force is subjected to it. And one of the most common applications of pressure is atmospheric pressure. So there are a lot of different units for pressure. You have 1 atmosphere is equal to 760 millimeters of mercury, 14.696 pounds per square inch, which is also equal to 101,325 Pascal. And then 1 bar is equal to 10 to the 5th Pascal, and 1 bar is approximately 1 atmosphere. So I'll explain what millimeters of mercury means because it has a very practical application. So atmospheric pressure is usually around 1 atmosphere. Imagine that. But for how they developed the measurement for millimeters of mercury, they got a little dish full of mercury and subjected and just put it outside because mercury is great because it doesn't evaporate or anything like that. It just stays put. It's pretty, it's not, it doesn't really move around too much. It's metal, it's pretty dense. So it's very good for this, it's very stable. So when the atmosphere pushed down on the mercury that was exposed to the atmosphere, there was this glass tube attached to the dish. So the mercury wanted to go to the area with less pressure, so they went to this tube in vacuum and it climbed up. So based off of how much pressure the atmosphere is exerting on there, determines how much the mercury goes up. So they determined that at normal atmospheric pressure, 1 atmosphere, the mercury rises to 760 millimeters up the graduated cylinder. And just one more thing to just make the concept of pressure make more sense, and apply it back to another concept, is that as the pressure, as the volume decreases, the pressure increases. Because as the volume decreases, that means there's less space to exert the force back on there. So every spot on the outside of the container has to experience more force. So as you decrease the volume, there's more pressure. This makes a lot of sense because as you start to squeeze a water bottle, like a plastic water bottle, it becomes a lot more tight because there's less space for the gas to exert its force on. So it has to exert more force per area, increasing the pressure. Thank you. I hope this made kinetic molecular theory make a little more sense.